moving on to a bit more blueprint. I managed to get this nice, it's a very simple trick, but I just want to show that. I have this nice little breaking ice effect going. So actually I forgot my torch. So I managed to make ice that breaks underneath your feet as you walk over it. So the section there in the middle is going to break. If I keep standing on a piece of ice, it will break more and more. So I'm just going to walk over it quickly, and it probably doesn't break too much. You can see actually there a piece broke down. So where you walk, it breaks automatically. So it automatically goes wherever you go. It's not entirely done yet. I need some more particles, I need some sounds, all kinds of other stuff. But it actually follows the path where you were. And if you keep standing somewhere, you will eventually fall down. The way I set it up is very simple again. Most of the things I do are actually very simple. I have this one mesh surrounding it that's actually modeled like this, so it's actually modeled as if it's a hole. And then the middle mesh is this one. That one I turned into a destructible mesh. So it's a destructible mesh, and it looks like this, divided in quite a few pieces, as you can see. My settings are this. I have damage thresholds. You can basically just read the settings if you want. Pause the video and read them. There's a physical material here with very low friction to make sure the ice slides better. And everything else here is pretty much default except the two materials. That's it. I added it in the level, and then what I did is I made a trigger here. The trigger has a radius which is about the size of the area that's gonna break. And the trigger basically says, it has a property, it has a variable. It says this ice mesh, so this destructible mesh. Sorry, let me show it here first. In the properties here, it has something called destruction mesh. So it basically says this mesh belongs to me. So it just identifies which one it controls. And then it passes that one on to the player. So when you step into the trigger, it will tell the player that the destruct variable in the player should be set to this mesh. So the player now knows on which ice mesh and destructible mesh it's standing, he or she is standing. And then in the player, what I do is I just apply an impulse every few seconds, or every half a second, I believe. And that's all I do, and it actually leads to the ice breaking as you walk over it. So let me get player. Here's my player. So this is connected to on tick. So this happens every tick. And it first checks, is this one valid? So it basically checks, is it occupied or empty? If you're not standing on one of these ice triggers, this one is not filled in. So it's empty, so it's not valid, so nothing will happen. But if it's filled in, it means you're standing on one of those triggers, so it's valid. Then it's gonna stop. It delays the ticking, but if you delay ticking, you basically stop it, and it only executes once every 0.5 seconds. So every half a second, I do apply radius damage to a destructible actor. The target is that one. And I take the player pawn, player location, -92, so somewhere around the feet of the player. And at the location of the feet, I apply 20 damage and a bit of radius damage. That's it. And that makes the ice break as you walk over it. Now, in general, we have tons and tons of blueprint, right? So this was shown in the previous videos as well. There's a lot of functions here as well, so this is not even an entire system. We have a lot of blueprint, really tons of blueprint. But we have been moving more and more to C++. Not really for reasons of performance, which is something I'll get back to in a second, but more for reasons of organization. So you can see actually one of the major things I took out here is the switch item thing. This is what I actually covered in one of my videos, making an inventory system in just Blueprint. Well, I did actually take the entire inventory out of Blueprint and we remade it in C++. And the reason is really to improve the workflow in Blueprint, reduce the chance of errors, those kind of things. It's not really about performance, right? And the first thing we did when we started doing this was we began moving variables out of Blueprint and into C++. Because let's say that the player has a variable that holds the body temperature of the player. Then the problem is, if you're in a different script somewhere, so let's say you're in a level blueprint, and you want to know how warm the player is, so what the body temperature is of the player, then you can't really get to that. I mean, what you would have to do is you would have to get the player pawn. You would then have to cast the player pawn to your type of player, or to whichever actor it is, but you have to cast it to whatever you're using, and then you would be able to access, okay, what's that variable in the player, so what's the temperature? That means that every time you want to do it, you have to use this cast. That both clutters up the blueprint, so it gets really, you get a lot more blocks in blueprint, nodes in blueprints than you need, but it also makes the blueprints more dependable on each other, because this blueprint is now directly going to call on this one. I mean, this has a direct reference to this, to the Solus player. So you get a lot more references connecting all of the blueprints. And we're not 100% sure, but we believe this both increases the chance that something goes wrong, like circular references, and that it might make the loading time slower, compile time slower, those kind of things. But again, I'm not 100% sure on that, but it is something we kept in mind. So what we've done is we first of all moved all the important variables to C++, and we made sure that you can access those from the entire game. So if I need the body temperature, I can just do Solus player body temperature, and I have the body temperature. I don't need to cast, I don't need to get it from anywhere. I can just instantly get what I need. And that's the first step we did when we started converting the blueprint over to more C++. Once that was done, we started moving events as well. So now, for example, I have the voice system. And this is my voice system here. The voice system basically plays lines of, voice. It basically plays one-liners. It's basically going to say, oh, it's so cold today, and that's it. So it's basically checking, what's the temperature, should I say something, maybe I should say something now, those kind of things. You know, that thing, however, is therefore playing lines of voice, but I need to be able to stop them, because what if you die, for example, while you're saying something? So I need to be able to instantly stop this system. In other words, I need an event that I can execute a stop on, like this. So what you would normally do, if you were to be just pure blueprint, is you would have a custom event, right? So you would create a custom event, and then the custom event you create, you would be able to access in another blueprint if you first cast it to that type. It's the same for the player. Let's just look at the player then. Let's see if I can find an event here that kind of makes sense. Let's see where I have one. Like here's a custom event, ladder exited. Right, so if I would want to execute that one in here, I would first have to do the cast, and then I would be able to do, ladder exited. Then I can call on the event. Again, then you need 3 blocks, 2 blocks more than you should be using, and it kind of makes things more complex. The workflow is kind of going down. So what we did instead is we're using these kind of generally available events. So you can see this one directly triggers this one over here. This is a CPP request. And Rama, or programmer, told me there's something very special about this. I have no idea what, but if you're interested in this, you might want to check up with him, because he said this was special the way he did it. But we now have a lot of events in any case that allow us to directly communicate from anywhere in Blueprint to anywhere else without casting in a very direct manner. And we're doing this through, we have about 100 of these variables and maybe another 40 or so of these events in there that are really important and that are available everywhere in Blueprint. But then we took it a step further. So as mentioned, we even moved our entire inventory system over. So you can see what happens now is this the logic where it normally happens. This is when you pick up an item. What happens now is that the item gets added to Solus inventory add item. This is a C++ thing. So this basically sends this item, goes in to C++, and then C++ takes care of the rest. So the system we're having now is that we basically make C++ handle specific parts of the functionality, like store this in your inventory, please. That's what it does. But all the functionality of like when it adds to the inventory, when it calls on it, how it uses it when it's called on, all that kind of stuff, that remained in Blueprint. So basically we offloaded all the complicated things all the stuff that's going to require tons and tons of nodes in blueprints to do right, or that might be really performance heavy. I did mention in the beginning we're not really doing this for performance reasons, but still there are some things that are really heavy for performance. And moving those over to C++ wouldn't be a bad idea. But we're keeping the logic in Blueprint, and I think that's a very important thing to do, because if you have a powerful system like Blueprint, it wouldn't be very smart, in my opinion, if you were to just completely ignore it. And over the past couple of months, I've seen a lot of programmers kind of struggle with the concept of Blueprint, because the programs seem to be kind of used to having to do everything in code, and they seem to be a bit of a barrier for them to learn Blueprints, which is kind of, in a way, surprising. I mean, I thought the artists and the designers were going to have more issues learning Blueprint than the programmers, but it almost seems as if the programmers are getting more stuck on Blueprint than the other way around, because it's so radically different for them. And it seems to be a lot of teams struggling with getting the balance right, like how do we combine like this whole Blueprint system with all the work our programmers are doing. So the way we've done it here again is we're trying to keep everything as Blueprint focused as possible, so we can actually make use of the power of Blueprint, because I mean this is a really powerful system, but we're offloading the complexity to C++, and I think that's the perfect balance. We probably have a bit more Blueprint than you should have still, but making sure that you're using the power of C++ but the flexibility of Blueprint, I think that balance is key in doing this correctly. A very good idea of that is our heat system. Let me see what I can add here. I have an actor, and the actor actually offsets the heat, right? So when you play, what normally happens, or actually the torch has it, let's just use that, it's these rings. These rings indicate how warm it is near the fire, how much the temperature is offset basically, or dampened, multiplied, whatever. Because normally you have a temperature. Right, you can see on the pocket computer on the bottom left, it's 0 degree if I'm standing here, 0 degrees Celsius. If I walk towards the torch, it adds up the more I walk towards the torch. So if I'm standing right on top of the torch, it's 11 degrees, if I can read it right, it's 11 degrees warmer than it is over here. So basically the world is checking the temperature, and I basically know what the temperature is at any single location in the world. I can basically ask it what's the temperature there in the corner, and it's going to tell me what the temperature is. And if I have multiple torches, then it would add those temperatures together. So let me cheat for a moment and get myself a torch. So now I have 2 torches. If I add them next to each other and I stand in the middle, I'll get like 20, 21, see. So now it's warmer, so it's adding it up. I've actually succeeded in getting that up and running entirely in Blueprint. So the whole aspect of it adding temperatures together, the whole aspect of checking how far the player is away from each source, all of that stuff I got up and running in Blueprint. But it did require me to do heavy stuff. Like I had to check all the overlapping actors, every frame basically. I did all kinds of weird stuff. I had lots and lots of Blueprint, lots of wires going everywhere in all directions, but I managed. But again, it took a lot of time, and it was far from clean, not that optimized either. So then what we did is that's a typical example of how we moved a specific thing that's kind of demanding to Blueprint. Let me open one of those related scripts. So you can see this one. This is the same kind of thing that's connected to the torch. We made a component, and that component visualizes like this. It allows you to say, well, how big it is, clearly, it's not that hard. And it allows you to say how much it should add to the temperature. So this is going to add 34 degrees to the temperature in the middle. You can also add some other stuff. As you can see, that's pretty much it. And then in Blueprint, let me open the stat system. The stat system is what we're using to calculate all the temperatures and all the stuff. You can see this is the stats. You know, so these are levels, like player leveling. This is sleep, more sleep. This is when you get wet from rain or water, those kind of things. Thirsty, how you calculate thirst, how you calculate hunger. This is the temperature, too cold, too hot, ideal temperature. So this is basically the body temperature calculation, those kind of things. We have one function here, which is the core stats update. This is the most important one. So if you look at that function, this does the core of the game basically. So first of all, it asks the atmosphere volume what the current temperature is of the volume you're in. So that's simple. I mean, that's standard blueprint. But then over here I have these new things. I have this one, gather all temperature sphere offsets relative to point. So you get the world location and then it outputs the different values. That's the stuff that this one does. So this one, if I say I want to know what the temperature is at this point, it will take the temperature it adds on top of it. So it takes the temperature of the world as it is, plus the temperature added on top by this actor. That's a typical thing of what we're doing in Blueprint. So we did that in Blueprint, but the rest of the functionality is still done. Sorry, we did that in C++, but the rest of the functionality remains entirely in Blueprint. The act of actually adding that offset on top of the temperature of the world, because this is the temperature of the world, the act of combining these two, all of that remained in pure Blueprint. Because if I have at any one point want to say, okay, but maybe, maybe the order should be different, or maybe there should be an extra step added to it, I don't want to have to run back to my programmer. I just want to be able to prototype it in here, try it out, and maybe one day we can move it over to C++. But in the meantime, I just want to try it out. And that's really key to what we've done. The same goes for the voice system, actually. It's the voice system that queues the lines. So what happens is that every time something happens, the system is queuing the line, right? So it basically, when you're very cold, then the system will queue a line that it should say something about the fact that it's cold. But it's not instantly going to play that line because you might already be saying something. So basically it builds up an array of lines to say in order. And the moment you're done talking about whatever you're talking about right now, it's going to take the next item in the array and play that one. That's quite a giant system to do in Blueprint. Again, we've tried doing that and it took a lot of time. It was buggy, it was hard to master. So again, that's a very specific thing. We move over to C++, but the entire system of like checking on bools and, when it speaks, when the actual act of speaking, this is the actual set sound and play sound. So this is the actual speaking itself. The delays, when he's allowed to speak. This one, for example, checks when he's allowed to speak. Again, all of that remained in Blueprint. But if you go back to profiling for a moment, I profiled the whole game, Blueprint especially, and I did find all kinds of issues. So normally with Blueprint, you can go really far and none of this is really a problem. Like 99% of everything I've done after profiling turned out to be absolutely perfectly fine. Wasn't heavy at all, so none of this is heavy. I checked all of it. It's all completely fine. But there were a couple of specific things that were really, really bad. First of all, how you're actually doing this. So if you want to profile your Blueprint, you need to make sure you're running the game standalone. So don't run it in the editor. It's really inaccurate. Make sure you run it without editor. Close the editor and just run the game. You can run the game if you start it like this. So you can see, you can make a shortcut. I did a bat file here, a batch file. It's kind of like the DOS way. It's very old, but you can also make a shortcut in Windows. But the point is, you make a shortcut to the editor executable, and then you have a space behind it, and then you have the path to your project. Again, there's a space behind it, then there's a dash, and you do dash game, which forces the editor to run in game mode instead. Well, then I set the resolution. You don't really need that, but the point is I set a resolution, and I also added save to user there. I'm not sure if you need that. This might be something we've done in our C++. And running it like this will run the actual game. If you then in the actual game were to type in the console start file like this, and then preferably not long after, like a minute or so maximum after you've started the file, you do stop file. You've recorded a profiling file of all mostly the code and the blueprint, so you can actually see what did what. Don't let it run for too long because it's gonna increase in size really fast. So just run it for like a few seconds, 10 seconds or so, and stop it again. But once you've done that, you will be able to find your files in Windows in the directory where you are in your project directory. So if I were to go to so this is my project directory, there's a folder called saved, and in saved you will now have a folder called profiling, Unreal Stats, and you got all of this stuff. So these are my previous tests, and you get that kind of file. If you were to open the Unreal Engine 4 front end, then I get this, and this, unfortunately it's very difficult to fit on the resolution of the recording, but this tool is basically found in the same place where you're finding the editor. So in this same folder, Win64, etc., you should also find a tool called Unreal Front End, or UE4 Front End or something like that. Let me check the exact name. Unreal Front End.exe. If you run that, you get this. It might look like this for you, but at the top it says Session Front End. Might look like this again for you. Then you have Profiler here, and you can do Load Profile. Load a profile, and you select the file you just generated. What we can see then is this. This is everything you recorded, and you can basically click somewhere in one of these in this area. And this is hard to fit on resolution. Let me change the window size a bit. At the bottom you would then see this. And here you want to go to game thread, frame time. Just keep on going basically. Game engine tick. You're basically looking for what has the highest number. You can see it's in milliseconds. This is the time spent in that frame on doing this one specific thing. So by adding up all those times together, you get the frame time. It means it takes 10 milliseconds or 12 milliseconds here to do the game logic. So this is mostly about the game logic, so blueprint code, that kind of stuff. So if you then do game engine tick, world tick time, etc., you get to the list of things that it's actually doing. And this is where it gets really interesting. This allows you to see what your blueprint is doing. I have to make the window quite a bit larger, maybe too large now. Hold on, it's kind of hard to fit this on a very small screen. Right, good enough. You can see here, out of the 10 milliseconds that this entire thing did, 7.9 is going to the character movement component. So most of the performance is going to this specific thing. You can see this is my blueprint as well. I can click on that and you can see what it does. It doesn't say much here, but it's about collision, it's about updating. So by doing this, it turned out, I investigated it, and it turned out that there were all kinds of things attached to the player, and those things that were attached to the player, they even had collision. So for example, the voice system, that was attached to the player, and the voice system had a box shape to it, and that box shape was overlapping with everything in the world. So basically what happens is every tick, the engine is going to check, okay, is this thing, is my box here that's attached to the player, that thing is just moved. That means I have to go recheck everything else in the world, if anything else in the world is now overlapping with the box. Basically the act of doing that made it really slow. So I removed the box, and I also took the PDA, which is for example really heavy for me as well. Reason why it's heavy is because it has a lot of attached components. It has about 40 to 50 components. It's basically all the text you can see is a component. That made it heavy as well, so I made sure that all of this stuff as well, it definitely shouldn't have any collision, and I made sure that it uses the parent's bounds, use attach parent bounds. That made it a lot faster, so doing that fixed basically my performance issue. It pretty much instantly fixes, but this shows the importance of checking what's happening. But then after that, so disregarding that one, you can see what else it's doing. So you can see, well, we have this and we have that. So this is basically all the blueprint I have. You know, this is the sky, for example, atmosphere and weather. That's my sky. Well, that only took 0.046 milliseconds. That means that my entire giant sky thing, which is this, you know, this only takes 0.046. It takes nothing at all. So it shows just how light it can be. Performance really is usually not the problem. It's very specific things that usually destroy the blueprint performance, not blueprint in general. And also, if you're uncertain about what takes performance, let's take the sky now, you can actually see the blueprint time, and you can see in quite a lot of detail exactly why it's slow. If you keep on clicking, eventually you'll get somewhere. It's a lot of sub layers, but you can basically see exactly what makes it slow. See, the heaviest part out of the sky is actually the fact where it's checking if you have to enable or disable the sun. that's basically the slowest. So if you know that function is the slowest, you can start optimizing specifically that function. You can even see how much time it takes to get the player pawn 0.001. You can see break vector takes that much as well. So you can basically see for every single block, every single node you use, how much time it takes to figure that one out. See, the fact that I do set temperature, set a variable, that takes this much. So this is a very good tool to figure out what's going on. Now we hit several problems doing this, or I found out several things more. I had a lot of things on tick, so I started scaling down on how much ticking I'm doing. For example, what we have nowadays is we're actually growing plants. When you pick up a plant from the ground, the game knows that spot is no longer occupied by a plant, and it will then respawn that plant, and the plant will then grow dependent on what the climate is in that area. So that means that every plant is aware of the temperature and humidity and all that near the location where it's growing, and it will use that information to figure out how quickly it should be growing. That turned out to be rather slow. So I have a blueprint here that controls that to an extent, I believe. I have a plant growth location. That's the thing I'm adding everywhere to figure out if there's a plant there or not. And that does this, for example. That basically checks if there is still a plant occupying that spot, etc. But then the real thing is in the item itself. So in the plant itself, which is a standard item, so we're using one blueprint for all the items, which ended up being rather big. It's going to check if it's a plant. So we have a function here that says control plant growth, which is running per tick, because you can see this one is tick, and this goes to here, and it basically checks plant growth control. So this is running per tick. It checks first of all if it's an actual growing plant, which is a function in itself. It's just a bunch of bool checks. And then it basically gets the temperature in the world. So it takes the incoming temperature and does all kinds of calculations on that. It adds all of them together to get a final outcome. And then it sets the play rate of a timeline somewhere, which is the timeline controls how quickly it grows. By changing the play rate of that, we control how quickly it's growing for real. So it does all of that real time. The problem is this was quite slow, because it basically was checking this, and especially other things like the overlapping and all that. It was checking it per tick. So I ended up using a lot more timers nowadays, and that seems to help a lot for performance. So for example, the stats in particular, they're doing this all over. Rather than doing weird loops like a line going all the way to the beginning again, or all kinds of other stuff, I basically do a lot of timers. So I can run it only once a second. I do this with all kinds of things. For example, when the ocean moves, it is supposed to pull along a couple of volumes, but moving those volumes turned out to be really slow. So I made a blueprint that moves the volumes up and down. So basically just moves this the actor location. It moves the volumes up and down, but it only executes this every half a second. So the volumes move up in steps rather than smoothly. Doing a lot of that actually saves quite a bit of performance. So bottom line, if you do what we did and you make sure you don't overuse the ticking, you move some of your stuff, especially the very heavy stuff, to C++, and you check the front end every now and then, you should be totally fine with having lots and lots of blueprints. We're not experiencing any problems at all anymore with blueprints. Now we've gone through those problems.